At the end of our previous example, we finished looking at our first ice table, which required us to use the quadratic formula to solve for x. We're going to continue with the same type of theme today, with a little bit of an exception. That exception answers the question, what happens when the quadratic formula simply doesn't work? Of course, quadratic formulas work well when you have an x squared term. In some cases in chemistry, though, what we're going to see is that we're not always dealing with an x squared term. We may have a cubic or a quartic function. There has to be a way for us to minimize the problem here and figure out what's happening. The question says, carbon monoxide is a primary starting material in the synthesis of many organic compounds, including methanol. At 2000 degrees Celsius, KEQ is 6.4 times 10 to the negative 7 for the decomposition of carbon dioxide into carbon monoxide and oxygen. Calculate the concentrations of all entities at equilibrium if 0.250 moles of carbon dioxide is placed in a closed container and heated to 2000 degrees Celsius. First step is to write down what we know. So we have a chemical equation showing the 2 moles of carbon dioxide decomposing into 2 moles of gaseous carbon monoxide as well as oxygen gas. The number of moles are provided as 0.250 moles, and the KEQ is provided at 6.4 times 10 to the negative 7. As with any problem you have in life, always figure out what you're given because that's your starting point. Once you figure out what you're given, you need to figure out where you're going, and that allows everything else in the middle to start filling in. So what we're trying to do here is calculate the concentrations of all entities at equilibrium. Equilibrium concentrations. So it's this row here in the ice table. As usual, that's going to be our target. We'll have some kind of change. Of course, we have some initial values. The initial values provided are only for the carbon dioxide. We're not told anything about carbon monoxide or anything about oxygen. Because we're only told about the one entity, we can safely assume the other two are not present. Looking at our mole ratio here, we're going to use 2 moles of carbon dioxide and produce 2 moles of carbon monoxide and 1 mole of oxygen gas. This means at equilibrium, we have 0.25 minus 2x, a 2x value, and an x value over here. So far, everything is standard. And in fact, we can take it one step further, and we can add in the next part, the KQ. So our KQ expression, as expected, would be KEQ is products over reactants. This would give us a 2x, because that's the concentration of carbon monoxide, and an x over here. If you're looking at this and you think something's missing, you're right. And because you know I have the ability to edit this video, I'm leaving something out temporarily. At the bottom, we have 0.25 minus 2x. All of this equals our K value of 6.4 times 10 to the negative 7. What am I missing in my equation here?
Maybe this screen can tell us something.
If you look back and you realize that I'm missing the rate law aspect, you're correct. Because this is a 2x and there's a 2 coefficient in front, the 2 tells us about how the ratio impacts the amount in equilibrium. It also tells us the rate at which that reaction occurs. So we have a 2 here that tells us about its relationship to change and tells us about how the reaction is occurring. Same with our reactant. We have a 2 over there as well. Suddenly we see this, and we realize we're going to get an x cubed term, or a cubic. This is going to be a mess. Take a minute, pause the video, and find out what this x cubed expression is, but don't apply any type of cubic solver to it. You should have this type of expression, and we notice that there's a massive problem here. The problem is we're dealing with something that's a cubic, and we need to solve for x. Again, we're not using a cubic solver. We're definitely not using a quadratic, as tempting as that might be, because we just learned how to do that and everything's great. We're not using the quadratic. We're going to take a closer look. We realize that all of this mess here happened because of that 2x. That 2x is a source of all of our misery at this point in time. Now, something else is very interesting to notice as well. We notice that that minus 2x comes from the amount of carbon dioxide that's reacting in this process. So let's take a closer look at what's going on in this process to see if we can maybe find kind of a cheat way around this, or a way that we can make an assumption that's going to make our life quite a lot easier. Remember, KQ is a measure of product concentration over reactant concentration. Although this analogy isn't perfect, if we took this value and convert it to a fraction, we end up with something like 1 over 1.5 million. That's important, and that's important because what we see is that very roughly the majority of everything we have is staying as reactant, and very few things are going to product. We could safely say that if 1 in a million pieces breaks off, that this part here, the minus 2x, is probably about 1/1,000,000th the size of 0.25. It's not going to be a significant amount. In fact, it looks like it's going to be very insignificant. So let's get rid of that and try and solve this problem without using the minus 2x. That's going to make our math much simpler. We can use our x cubed, take the cube root, and we should be on our way in no time. Of course, this is an assumption. We'll have to discuss that a little bit further in a minute. So let's see exactly what that looks like from a math perspective first. What we have is our KQ value being 6.4 times 10 to the negative 7, and that's equal to our 2x squared times x, that part remains the same, and it's now divided by 0.25 squared. This means we get 4x cubed equals 4x cubed equals 4 times 10 to the negative 8, or x, taking the cube root of both sides, is 2.15 times 10 to the negative 3. So if your first thought is, how did we just get rid of part of our formula and still have the correct answer? You're not alone. This takes a little bit of time to wrap your head around. So let's recap in blue. So what we saw over here was that we had a situation where the amount of x breaking off is very, very small. It turns out that the minus 2x that we have is very small, and we can likely ignore. We're making a hypothesis here. We're saying we're going to ignore it, but we don't know if this is a valid assumption. We're ignoring it because we see a very small amount breaks off over here, but this is something we're going to have to check or validate later on. So we're going to check our work. So to check our assumption, what I'm going to do is I'm going to take 0.25, which is my equilibrium value, and subtract 2 times the value of x, 2.15 times 10 to the negative 3. When I do that, I end up with a value of 0.2147, 467, if you check on your calculator. And this is about a 1% change. In chemistry, we're okay with up to a 5% error as long as it saves us a bit of time, because there's error associated with measurements. You know this from your lab. The graduate cylinder, the beaker, the thermometer, everything has some error associated with it. So if we get an answer within 5%, we're generally okay with that, because the amount of work to use a cubic solver just isn't worth our time. Our final step that we validated our x is to take our x value here, substitute it in, and finish up our equilibrium expressions over there. Any questions about this, let me know. It's quite a bit of thought process around this. We're going to see this more in acids and bases. If this example makes sense, continue working on with the blue examples. Once you're comfortable with that, we're going to start looking at KSP in the near future. As usual, any questions, post them or ask me. There'll be a tutorial session this Thursday as usual, and I look forward to hearing from you.